So the next talk will be given by Aurèle Barrière. It is one of the distinguished papers this year, with title Formal Verification for JavaScript Regular Expressions, a Proven Mechanized Semantics and its Applications. Yeah.
Thank you. And this is joint work with Victor Deng and Clément Pit-Claudel. And I know that judging by the title of the talk, it looks like I'm about to tell you about regular expressions, but I'm not. Because this is a talk about JavaScript regular expressions, and these modern regular expressions, or regexes for short, are just different from your traditional regular expressions. And they are different for several reasons. First of all, they are not regular anymore, because we added some new features that increase expressivity, and it's actually quite easy to build a regex that will match the language of duplicated words, a language that is famously non-regular. But also, the matching problem itself is different. With a traditional regular expression, the matching problem is simple. We're trying to decide whether or not a given string belongs to the language recognized by the regular expression. It's a simple yes-no question. With a regex, however, things are different. Given a regex and a string, we're trying to find a substring that is matched by the regex. And if there are multiple ways to do so, we should return the substring which has the highest priority. Now, different regex languages have different ways of expressing which is the match with the highest priority, but most of them today mostly agree on what we call backtracking semantics, meaning that we should return the match that would be found first by a backtracking algorithm. This means, for instance, that the first match in the string has priority, explaining why if I'm trying to match D or B on that string ABCD, it will return B and not D. But also, this junction is no longer commutative because we're going to try the first branch first, meaning that R1 has priority in that example. And so if I'm trying to match A or AB on the string ABC, I'm not going to return the longest match, I'm going to return just A. And finally, whenever we have quantifiers like the star or the plus, the priority should be to try and iterate them as many times as possible. Meaning that in that example, of course, B star is going to match all of the Bs. Now, because of these new features and this new matching problem, modern regex semantics have become increasingly and surprisingly complex and subtle. We have plenty of features and edge cases. To make things worse, each modern regex language is different, meaning that, for instance, JavaScript regex semantics are not the same as Python regex semantics. If we take a look specifically at JavaScript, in JavaScript there is an official document, an official standard telling you how to execute any JavaScript program, and this is called ECMAScript. And this standard contains a full dedicated chapter to JavaScript regexes. So we have a huge dedicated regex chapter, and it's more than 33 pages of specification describing with pseudocode and English how to execute a JavaScript regex with a backtracking algorithm. So if we want to reason about those modern regex semantics and those modern regexes, we would need semantics that are both faithful to a real-world regex language, with all of its subtleties, and that are also practical for formal verification. And this is precisely what we do in this work. We provide faithful and practical semantics for JavaScript regexes that we mechanize in Rocq. And to show how practical they are, we provide multiple applications. We formally verify some regex equivalence, and we verify a matching algorithm. Now, those two qualities, faithfulness and practicality for formal verification, can sometimes be at odds with each other when designing formal semantics. And we can even see that in related work about JavaScript regex semantics. In fact, there has been multiple kind of attempts. One of them is actually our previous work in collaboration with Noé de Santo. And this was called Warbler. And in that project, what we did is that we did a line-by-line translation of these big regex chapters that I was showing you before. And so we have thousands and thousands of Rocq lines where for each pseudocode line of the standard, we wrote an equivalent Rocq line. Now, clearly, this was faithful to the standard because for each line, we have an equivalent line. But also quickly, this becomes not really practical for formal verification. Even though we managed to prove a few properties with Warbler, some of them are quite complex to prove. Because we have like thousands of lines of a big Rocq fixed point and so on. But of course, when we think about semantics for regular expressions, we think about the nice inductive style semantics that we have all seen before. And we could simply try to extend that with JavaScript regex features and this new matching problem. And in fact, this has been done before multiple times in other papers. Now, of course, the question is it faithful? Sometimes it's difficult because it's very different from that official JavaScript standard. And in fact, a few years ago, there was this semantics that had to be fixed 1 year later because some feature was incorrect, and there could be other problems. And also, while this is clearly more practical than Warbler, we show in this work that we can even do better and have some properties that are even more practical for formal verifications. So let's just quickly recap about some of the features that we have to deal with in our semantics. Of course, we have all of the traditional features from regular expressions, but we also have so many different ways to match characters, like character classes and so on. We also have plenty of ways to do iterations. We have the star and the plus and others. This one, for instance, is going to repeat a regex from n to m times. And then we have an interesting feature that we call a capture group. So in modern regexes, every time you have a sub-expression inside parentheses, the engine should not only return the substring that was matched by the whole regex, but we should also return the substrings that were last matched by each sub-expression inside those parentheses. And so in that particular example, I have a capture group because I have B star inside parentheses. And so the engine should tell me that the whole regex matched AB, and that this capture group last matched the string B. And so that is the expected result. We also have another very interesting feature, which is called look-behinds. I won't go too much into details, but it allows you to match the string backwards. So you had some position in the string, and then you have to read the previous character and then the previous character again. So that we have to take into account when designing the semantics. And of course, we also have look-aheads, anchors, back references, and so many different flags that can alter the behavior of matching. Okay, so how are we going to give semantics to all of these different things? One of the insights in our paper is that the best way to reason about those backtracking semantics is not with a backtracking algorithm. Instead, we're going to define another kind of big step style inductive semantics that we like, but with something a bit special. We're not going to relate a regex and a string to some result, like the result of matching. We're actually going to relate a regex and a string to something that contains a bit more information that we call a backtracking tree. And this backtracking tree, you can think about them as a sort of execution trace of a backtracking algorithm on that regex and that string. So here is an example. This is a backtracking tree of the regex A or C inside a capture group or AB on the string AB. And whenever you want to try to match this regex, you have to do a choice between matching the capture group on the left or matching AB on the right. And so this is why our backtracking tree begins with a choice node at the top. And then the branches of the tree are ordered by priority. So we put on the left what has the most priority, in that case trying to open the capture group and match what's inside the capture group. And on the right, of course, we simply try to match AB, and then we find a match. Whenever we go inside the capture group, so on that side, we again have a choice between trying to read A or C. If we tried to read C, we would fail because there is no C in the string, and so that's why we get a mismatch. But of course, if we try to read A, we could simply finish, close the capture group, and return a final match. Now, before I tell you how we build these backtracking trees, I want to tell you why we like this kind of semantics. And one of the big advantages, of course, is faithfulness, because we have a huge Rocq proof that states that the leftmost match leaf of this tree is always equal to this Warbler mechanization, this huge line-by-line mechanization that we did. And so if you trust Warbler, then you can also trust our semantics. Also, one very important feature for practicality is the fact that this actually contains more behaviors than a backtracking algorithm. Because a backtracking algorithm typically starts after finding the first match. It would never even consider the other possibilities. And in that example, it would never even see the second branch and the third branch. But in the later slides, I will show you how having those extra behaviors is actually great to reason about sub-regex equivalence and to reason about some matching algorithms that will explore those extra paths that a backtracking algorithm won't see. Finally, a third advantage, and I know this slide might look a bit scary, but actually with only 21 nice inductive rules, we can completely isolate the control flow of all JavaScript regexes. And so this is complete for ECMAScript 2023, and we only use those inductive rules. I want now to take a closer look at the semantics, and we will begin by taking a closer look at the semantic states. In our semantic state, we have a couple of things. We first have this L, which is a list of things that we need to match sequentially. So initially, this is just the regex you want to match, but then this will increase as you do the matching. And the things are mostly regexes, but we will see that we can add some other things too. Next, of course, we have an input and a position within that input, the string, of course. We have a value of the capture groups that we will need, and we have a matching direction because, as I told you before, there is one feature that allows you to go backwards. So this can be either forward or backward. And next, we can look at one of our semantic rules, and I suggest looking at the rule for the star. So let's say that in my list of things to match, the first thing in that semantic state, I have r star followed by some other list. We want to also to match something after the star, but let's focus on the star. Now, clearly, every time we have a star, we should have a choice, because we can choose between iterating that regex one time, or maybe more, or we could choose also to match nothing with that star and just skip it entirely and go on with whatever is left. So, of course, in our tree that we evaluate to, we have a choice node and we have two subtrees. And the tree on the right, the one with the less priority, is quite easy. It should be the tree that corresponds to matching L, whatever was after the star. Now, the tree on the left is a bit more complex because, of course, we decided to iterate the star, and so we should match the regex R a first time, and then we should match the star again because we can do more than a single iteration, and then, of course, we should match L, whichever was next after the star. If we stop right there, there will be an issue if you're trying to match a regex like epsilon star, it will not terminate. But the good news is that the JavaScript semantics tell you how to avoid those cases. It tells you that you should check after each iteration of a star if you have made some progress in your inputs compared to when you first entered the star. And so in our list of things to do, we also add this kind of check things that will cut short the branch of the tree if you have not made any progress, and otherwise will keep matching and keep matching. And so this is just one of our rules. Of course, this is very simplified because actually we need to reset some capture groups. We need to take into account the greediness or laziness and maximum or minimum number of iterations. But this is the main idea that we saw for the star. And now that we have these nice semantics, we can actually use them to reason about some things. And one of the applications that we verified is equivalence. And we'll see that we need to define what it means to be equivalent. Regex equivalence has multiple real-world use cases. For instance, it is used in some regex engines, but it is also used by some regex optimizer to try and simplify regexes. So formally, when is it the case that two regexes are equivalent? Now, a naive definition, the most intuitive one, is to say that two regexes are equivalent when given any string, they return the same result. And that seems to be exactly what we want out of equivalent regexes. However, this definition is not entirely satisfying to us because this definition is not a contextual equivalence, meaning that you can have sub-regexes that are equivalent, but if you put them into a bigger context, then finally the bigger regexes are not equivalent anymore. And we can see that on an example. Using that definition, epsilon or A is clearly equivalent to epsilon or B, because for any string, they will simply match the empty string because epsilon is on the left of the disjunction, so this has priority. But of course, if we put them in a bigger context, like C epsilon or AC and C epsilon or BC, you will find different results. Because, for instance, the first one will find a match on the string CAC, but the second one won't. So if we want to try and fix this to get a contextual notion of equivalence, what we can do is take a look at the backtracking trees of those two bigger regexes on that string CAC. And if we zoom a little bit on the subtrees that correspond to executing the sub-regexes epsilon or A or epsilon or B, what we might see on that first tree is that the only match leaf that we can see used the second priority way of matching the sub-regex, not the first one. And so if we want to get this contextual equivalence, we will need to reason not only about the top priority way to match a regex, but also about all of the many different ways to match that regex. The good news is, of course, our semantics is designed to showcase all of these behaviors, and so we can simply do that, and we can do a new, stronger notion of equivalence, and we say that two regexes are equivalent when for any string, if we take the backtracking trees of those two regexes and that string, we will have the same list of match leaves at the end of the trees. Again, this is very simplified. You can actually remove some leaves, but this is the main idea. And we can then prove that this is actually contextual. And so if you have two subregexes that are equivalent using that notion, then even in a bigger context, they will be equivalent. And this allows you to reason locally about subregexes. Using these definitions, we could actually verify some equivalence from the real world. And so, for instance, we looked at a JavaScript regex manipulation library that is called regex3. And this library contains an optimizer. And so in this optimizer, they do the following optimization, where if they see the same regex quantified twice, they will just merge the two quantifiers by adding up the minimum and maximum number of iterations. And this looked completely correct initially, but of course it's not. We found some issues, and we also looked at some conditions under which the optimization can be performed. Interestingly, this depends not only on min1 and max1 and so on, this also depends on the matching direction, meaning that sometimes you can perform the optimization only when inside a look behind, and sometimes you can perform it only when outside of a look behind. Another application that we verified is actually a matching algorithm, and we decided to verify what we call the PikeVM algorithm. You can think about this algorithm as an extension of NFA simulation, but extended to support backtracking semantics and capture groups and other features. So what this means is that we are going to compile the regex down to an NFA, an extended NFA with some priority edges. And then the algorithm is going to find the top priority path in that NFA that corresponds to the string. This is linear time algorithm. It supports most regex features, and this is used widely in Rust and Go, and even for JavaScript, because V8, the engine of Google Chrome, for instance, contains an optional engine that uses the PikeVM. But despite being widely used, this is also quite tricky to get right, especially for JavaScript. 2 years ago, actually, we showed that the usual way to do the PikeVM is incorrect for JavaScript semantics because it has a unique way to check for progress in stars, the things that we were talking about before. The good news is that we designed a new NFA construction and changed the algorithm a bit. And with this new construction, at least it should work for JavaScript semantics. And now we wanted to prove it. Of course, we have a lot of challenges in that proof. We, of course, have to prove compilation correctness because we're going to compile that regex down to this NFA. This NFA is actually going to be represented with a bytecode, so we need to verify all of this. Also, this PikeVM has quite a peculiar execution order. It's going to do a mix of breadth first search and depth first search, so we need to prove that this is going to return the top priority match. Also, in order to be a linear time algorithm, this algorithm is going to prune some path of the NFA when it corresponds to a configuration like an NFA state and a string position that it has already seen. So we need to prove that we're not going to miss any match this way. And finally, because we modified it for JavaScript semantics by changing the way we check for progress, we also need to prove that this is correct. Let's focus for a short while on this exploration order. And one of the key insights is to say that if backtracking algorithm corresponds to a depth-first search inside a backtracking tree, then surely this PikeVM exploration order must correspond to some exploration strategy on a tree. And this is precisely that algorithm, this exploration strategy of a tree that we use in our proof. We write down an intermediate algorithm that works only on a tree and that does this kind of exploration strategy. So it mixes a depth-first search and a breadth-first search, and it is also allowed to prune subtrees, just like the PikeVM algorithm was pruning some paths of the NFA. Let's look at an example. Let's say that we have this backtracking tree of the regex A star or A followed by B on the string AB. And so our algorithm is just going to take this tree as input, and it's going to do a depth-first search until it finds a read. And then it's going to explore other branches until it finds reads. And when we have found all of them, we're going to move on in the string and then do another depth-first search until we find another read. And then we do the same for the other side. But then on the other side, we realize that we are seeing a subtree that we have seen before. And so this subtree is going to be pruned entirely, and we're not going to search among it anymore. Finally, we can return and finish the algorithm by finding this match leaf. Now, it's very convenient that this has the same exploration order as the PikeVM algorithm, because the first step of our proof is then proved by simulations that those two algorithms always return the same result. And then finally, what we can do is prove that this exploration strategy always returns the first match leaf of a backtracking tree. And conveniently, this proof has nothing to do with bytecodes or NFAs. It's just a proof about trees. Finally, of course, because we have connected our semantics to Warbler, we can also connect this result, meaning that we have a full correctness theorem that relates the semantics of this PikeVM algorithm to the actual ECMAScript standard that describes what JavaScript should do. Now, those semantics and these proofs are only the first step of a bigger project, because now we would like to develop what we call Linden, a formally verified linear time engine for JavaScript regexes. Now, of course, we have multiple things to still do. We have to provide verification of an implementation and not just a verification of an algorithm. And then we have many optimizations and other algorithms that we should try and verify. We could also extend this PikeVM algorithm, because 2 years ago, we showed that specifically for JavaScript semantics, it is possible to match in linear time unrestricted lookarounds. So we could also add that to our existing proof. And of course, we would like to do more equivalence proofs to have a full verified JavaScript regex optimizers. These backtracking tree semantics can also be used in other ways. We could use them for other languages, because each language is different. And we are also verifying right now the complexity of different subsets of JavaScript regexes. Now, some of these projects are already done. Some of them are ongoing. And for the rest, we would love to hire new students, either in Switzerland or in France. So feel free to reach out. Thank you.
Couple of questions. Any questions in the audience?
Hey, thanks for the nice talk. Your new equivalence semantics, do you know whether this is equivalent to the previous observational semantics inside of a context?
So we can prove that this implies observational equivalence under any context. But then there is a very interesting question of, is this the weaker possible equivalence that would verify that property? Mm-hmm. It's not something for which we have a proof, and our current intuition is that it could be the case, but that it won't be the case for a new feature that has been added now since 2023, which is duplicate capture groups. And I think we would need to first adapt this to support duplicate capture groups, and then maybe we would have the weakest possible equivalence relation that satisfies this property.
Thank you.
Any other questions? Yeah.
So thank you for the nice talk. I would like to follow on Damien's keynote in the morning. So how much is this reusable for the other flavors of regular expressions like Python, .NET, and stuff like that?
This is an excellent question, because this is one of the projects that we are working on right now. It really depends, but mostly we believe that this can be used for many other semantics. Clearly, .NET, for instance, we were looking at it because it checks for progress differently, but it seems like we could also support it. We could also support some flavors of longest match semantics just by looking which of the branches goes the farther. There are some of them that are quite surprising. For instance, the Java semantics uses backtracking semantics everywhere, but not inside look-behinds. And so for this, we still need a bit of work to figure out how we could adapt it. But so far, everything seems to point to the direction that it should be possible.
Thank you.
Thank you.
All right. Let's thank Aurèle again.